So it's a pleasure to have with us in this stormy winter day, Yifan Wang from Harvard University. He will talk about the marvelous defects and anomalies in quantum field theory. Thank you. The floor is yours.
Thanks for the introduction, and thanks for the opportunity to speak here. And I hope everyone is staying safe during this snowstorm. So I'll be talking about something about defects and anomalies in quantum field theories. And in this talk, I'd like to convince you that despite what their names may suggest, defects and anomalies are actually quite important objects and interesting objects in quantum field theories. And by exploring the intricate interplay between defects and anomalies, one can make quite general, non-trivial statements about like non-perturbative dynamics of strongly coupled systems. So let me start by remind you what defects are. So actually, if you think about it, these defects are really like ubiquitous in quantum systems because realistic quantum systems will come with finite size. Having a finite size means that there's boundaries. So in some cases, the effects of boundary can be neglected for the particular physical process of interest, but in other cases, these boundary effects may not be neglected. So one well-known scenario where this happens, where the boundary effect is important, is in this Kondo effect, which is well studied in the 1960s over the span of, I don't know, 30, 40 years. Okay, so in that setup, what do you consider is a piece of metal, conducting metal, say copper. And as you probably all know, that as you lower the temperature of a conducting metal, the resistivity are supposed to decrease. This is because potential resistivity are coming from scattering between the electrons and phonons in the metal, and also between electrons themselves. But both effects are suppressed as temperature is lowered. So you expect the resistivity to drop monotonically as you lower temperature. But it was observed in the 1930s that in the presence of some kind of magnetic impurities, for example, coming from iron atoms in the copper, that there's an anomalous dip. There's an anomalous dip in the resistivity plot as you lower the temperature. And furthermore, the resistivity rises again as you lower temperature further. Okay, so in this case, clearly the effect of the impurity becomes important in the low temperature phase of this conducting metal. And similar important examples of defects also show up in high energy physics. For example, as the world lines of heavy charged particles propagating in some medium. So one particular example is the propagation of some heavy quark in the quark-gluon plasma. Okay, here is a photo I took from some website for RIC. Okay, and in condensed matter systems, this kind of defect also shows up typically as boundaries of lattice systems, and they are important. For example, when we want to say compute the Casimir energy between two plates of a lattice system, and the boundary condition will play an important role. And lastly, in string theory, these defects shows up as deep rings. More precisely, they show up as boundary conditions from the Walshy perspective. So the natural playground that we want to explore to study these defects is going to be quantum field theory. Well, the reason is because quantum field theory has been such powerful and versatile tool to study quantum systems. And this is well proven by its description of, say, scattering process in, a particle scattering in QCD to, say, quantum Hall effects in graphene. And more recently, it helped to shed some new lights on black hole dynamics, thanks to the ADS-CFT correspondence. So we would like to extend the framework of quantum field theory to incorporate these defects. So to do that, we should first remind ourselves that the basic observables in quantum field theory are the local operator algebra, or in other words, correlation functions of local operators and scattering amplitudes with external states that are created by these local operator insertions. Okay. So how do we extend this? Well, the extension is quite natural. So instead of considering local operators, we should allow us to consider operators defined on some higher dimensional submanifold of your spacetime. So suppose you have some d-dimensional quantum field theory, and you can consider some p-dimensional submanifold sigma. Okay? And on that sub-manifold, you can define some defect operator, which I'll call curly D. And the defect operators can be defined straightforwardly when your theory has some Lagrangian description. For example, as order type defects, which generalize the well-known Wilson lines. In these cases, the defect is defined by some exponentiated integral of some functional of the bulk fields restricted to the defect world volume sigma, okay? P-dimensional in this case. There are also disorder type defects, which may be somewhat less familiar. And there are, for example, they include, for example, the Tuft lines and more generally some twist operators. And these operators are defined by modifying the path integral, by modifying path integral through imposing some boundary condition of the bulk fields at this defect world volume sigma. Okay, and more generally, the extended operators, say in the absence of the Lagrangian description, can be abstractly defined by the kind of symmetry that they break, the kind of symmetry they preserve, and by correlation functions that involve this defect operator and other local operator insertions, and potentially other defect operator insertions as well.
Can I ask you a quick clarifying question? So defect operator is something that when you act on a vacuum state creates the defect, or it's something else?
So when you act on a vacuum, it will create a defect state. So that's going to be a particular state in your Hilbert space. So you can expand that state into your favorite basis.
Okay, thank you.
Right. So in CFT, you can also do the radial quantization. In that case, you can expand the defect into local operators, because in that case, you have a state operator correspondence. Right. So one explicit case is the relation between the Carty states or Ishibashi states and the local operators in the context of 1+1 dimensional CFT. Yeah, thanks for the question. So yeah, I should say that whenever you have questions, feel free to interrupt. Okay. All right. So just to put us into the context, like I told you some examples on the first slide, which involve defects in interesting quantum systems. How are they described in the framework of quantum field theory? So this Kondo effect, the magnetic impurity in the Kondo effect, is famously described by certain defect lines in the SU2 WZW model, chiral WZW model, which models the spin degrees freedom of these conducting electrons and the impurity. Okay. So you can isolate the spin degree freedom, and that part of the system is described by a defect line in the WZW model. And correspondingly, in a high energy context, the world line of these heavy charged particles, such as the heavy quark in the quark-gluon plasma, can be described by Wilson lines, or more generally, Wilson-Tuft lines in gauge theories, or for example, in QCD. In the quark-gluon plasma, it would be QCD at finite temperature. And lattice system with boundaries and D-branes, they can be described by boundary states. And in the conformal case, which I'll describe, they correspond to certain things called Carty boundary states. So, well, in fact, these extended operators are not just useful for describing defects in this realistic physical system. They're also quite important in giving a complete abstract formulation of quantum field theory. Okay, so there are several reasons. Okay, so first of all, the topological defects, which are a special class of defects, which are invariant under infinitesimal deformations, they give rise to a natural generalization of symmetries. This has been explored in a number of recent papers, including our work. And one particular kind of generalized symmetries are the so-called high form symmetries. And for these symmetries, the charged objects are not going to be local operators. They have to be extended defect operators. Okay, so to see the effect of these generalized symmetries, you necessarily need to consider these defect operators. Okay, and in particular, a kind of defect operator that can be put into this context is the Wilson line operators and Tuft line operators, which are charged under the so-called one-form symmetries. And those operators, as you may have learned, are important other parameters for phase transitions, for example, for the confinement, deconfinement phase transitions in QCD-like theories. And furthermore, these defect operators are generally sensitive to global structures of the theory. So it's known that, for example, there are finite class of extended QFTs, which by definition is QFTs, with a specific specific set of consistent defect operators, there's a finite class of such consistent theories with identical local operators, but distinct defect spectrum. So a particular case in QCD-like theories have been explored in this paper.
Can I ask you again, just clarifying question to
Yes.
follow? So suppose I have just a simple scalar field.
Yes.
A real scalar field with a potential phi square minus v square squared. So that has a domain wall solution, which is a topological defect, well, in conventional terminology at least. So are you saying that there should be some extension of that quantum field theory further to for description of that defect, or this is just a new operator, some non-local operator that is being looked at in the context of that field theory?
So in that context, when I say extended QFT, I mean to classify all the kind of allowed domain walls that you have. So the example that you mentioned is one particular choice, right?
Sure, it's one particular solution of that theory, right? That's
well. So by a theory, I mean a theory that's defined an arbitrary, spacetime manifold. So you can consider the configuration that that correspond to your domain wall, but you can also consider other phases. So by a theory, I mean the theory that describes the various phases of this. Yeah.
I mean, if I wrote a Lagrangian, let's say I wrote a Lagrangian and it's M4. My theory is on M4 with a given Lagrangian, right? I can classify that all the phases that there are in that theory.
Right.
So I guess what I'm asking is that in that context, in that concrete context, what is the extended quantum field theory by these new operators that you
So you are considering the case where you have the phi square with a minus sign. So you have a domain wall solution. That's what
it's phi square minus v square squared for positive definiteness. Yeah.
Right.
I have a domain wall solution.
Yes. So in that case, the theory, that's right. Right. Yes. So you're right. Then in that case, it's less interesting. So you just have this solution, right? But for example, if you consider gauge theories, there are just different line operator spectrum that you can have for a given gauge group.
But that's what I'm trying to understand. That's why I brought up this simple theory. So some non-local operators that you are introducing, I mean, they might be interesting by themselves, but these are operators in the quantum field theory, as I understand. I mean, correct me if I'm wrong. I'm just trying to follow the logic.
No, you're completely right. But I'm saying there are distinguished choices you can make to have a self-consistent set of defect operators. So you can make one choice. You have a set of defect operators which are closed under fusion, OPE with themselves and OPE with local operators. That's one choice, but there may be distinct choices you can make with the same local degrees freedom. That's what I meant by the last one.
Okay, so you're thinking of some kind of algebra for those different defect operators.
That's right. That's right. So you can think about you have extended operator algebra that involves local operators and also defect operators, and there are distinct choices you can make to have closed algebras, given the same local operator algebra.
Okay, thank you.
Yeah, no problem. Thanks for the question. Okay, so given this defects, how do we, given this definition of defects in quantum field theory, how do we actually study them to compute some physical observables? Okay, so of course the first method that comes to mind will be this conventional perturbation theory that we all learned from QFT 101. So this involves computing Feynman diagrams, for example, of this type for some boundary defect. And this is actually the kind of diagram that's relevant for Kondo's solution to the Kondo effect in the 1960s. Okay. But in general, this kind of perturbative method is only valid, is only possible in certain cases when you have a Lagrangian, right? If your theory does not have a Lagrangian, we don't know how to write down the Feynman rules. And even if you have a Lagrangian and Feynman rules, this perturbative computation can also break down at a certain level in the loop in the perturbative expansion. And this is what happened in Kondo's computation as well. It's known as the Kondo problem. So Kondo's solution solves the dip of the resistivity, but it also points out that there's some anomalous divergence in the resistivity as the temperature lowers further beyond the dip. Okay, so this can be seen from the fact that the effective coupling between the impurity between the magnetic impurity, the iron atom, and the electron, free electrons in the copper, the effective coupling actually blows up as you lower temperature all the way to the so-called Kondo temperature. The resistivity roughly goes like this: effective coupling squared, and so tells you that the resistivity, if the computation is trustworthy, it actually blows up. But this is completely doesn't make any sense, and also contradicts with the experimental result. So some new non-perturbative method have to save this computation. Okay. So what kind of non-perturbative methods do we have? Well, the Wilsonian RG is very important. As we learned from quantum field theory, the Wilsonian RG is an important idea. The Wilsonian renormalization group is a very important idea for the formulation of QFT beyond perturbation theory. Okay, it gives a conceptually beautiful idea of how strongly coupled IR physics, which describe the system at low energy, large distance, emerges from could be some very simple UV description. Okay, and also provides this beautiful effective field theory approach to describe the IR physics. But in practice, this RG analysis is very messy and difficult. In one-dimensional systems, you can work this out quite concretely using numerical method, which is also what Wilson did in the 60s. But for higher dimensional cases, this is very difficult. In particular, one complication comes from the fact that there's a non-trivial rearrangement of the elementary degrees freedom when you compare the IR physics to the UV. So one case where this shows up in the context of QCD. So in the UV, the elementary degrees of freedom are described by weakly interacting quarks because the theory is asymptotically free. But in IR, the fundamental degrees of freedom are described in terms of the mesons and baryons, which are bound states of the quarks. Okay, so they are just very different beasts. And the effective description, it's not possible at this point to derive the effective description of these guys from the QCD in the UV. So to make this RG picture more intuitive, this is some picture that one can have in mind. So imagine you have a space of QFTs labeled by various couplings. Okay, the RG paradigm let us to view this potentially flat space of couplings, a space of QFTs, as like a mountainous landscape. Okay, with various features. In this picture, this green lines with arrow correspond to the RG flow, and you have these peaks, you have this saddle points, you have these basins, and this correspond to fixed points of the RG flows. Okay, and this saddle points can have, for example, stable and unstable directions. Okay, and to solve the IR physics, for example, to solve the IR physics associated with some UV fixed point, the IR physics associated with some UV fixed point, there are different ways to approach this problem. It's certainly more sensible to study the IR fixed point instead of the UV fixed point if you are interested in effective field theory around this region, because this is makes much more sense to extrapolate from here than from here. This is also why perturbation theory breaks down when you want to do perturbation theory around this point. Okay. So one way to solve the problem is to directly attack the IR fixed point. And the IR fixed point has this enhanced symmetry, which is described as CFT, which I'll say a little more. And this will be one approach to proceed. Another approach to proceed is to instead look for RG invariants, okay, along these flows. And because these are RG invariants, you can compute these quantities using the UV description. And because they're invariant, they give automatically some prediction for the IR physics. Okay, and these quantities will be given by so-called Defect anomalies, which I'll define. Okay. So let's first talk about the first approach, which is the direct study of the IR fixed point. So as I mentioned, this fixed point in unitary theories are expected to have enhanced conformal symmetry. And they are defined by, and the corresponding theory is given by a conformal field theory. These conformal field theories are universality classes of RG, and they capture critical phenomenon at second order phase transitions. And a typical example is the case of the water, as we all know. If you look at the phase diagram of water, you see that at a certain critical temperature, there's a critical phase that appears. Okay. And the fact that these are kind of universality class means that the same critical behavior also appears in other models of the same dimension, such as the magnetization of some uniaxial magnets, as well appears in the quark-gluon plasma at the critical temperature. Okay, so the claim of universality class, the claim of universality basically says that the critical behavior of all these systems and many others are governed by the same CFT known as Ising universality class, or in other words, the Ising CFT. This universality class, or the CFT themselves, are strongly constrained by the symmetry that they preserve. So in this particular case, it will be some SO3, 2 conformal symmetry. And in general, it will be some SOD, 2 conformal symmetry for a d-dimensional fixed point. And for this CFTs, there's a very direct non-perturbative method to solve its correlation functions known as the bootstrap program. This program explores the constraints from conformal symmetry together with unitarity and the so-called crossing symmetry, which is basically a consistency condition coming from the OBE of the external operators. And then after you have solved a certain amount of information at the CFT, you can then extrapolate to determine the EFT, the effective field theory, around this fixed point by doing conformal perturbation theory. And this is one way how, well, this is the modern way of how the quantum problem is solved. Okay, so there's no divergent coupling if you do this perturbation theory from the IR fixed point, okay, which corresponds to a particular boundary condition, conformal boundary condition in the WZW model. Okay, so one of the most important observables at the CFT are the conformal anomalies. Okay, so what are conformal anomalies? And this is coming from one of the hallmark of conformal symmetry, the stress tensor. So when you have a conformal field theory, the stress tensor is another current for translation symmetry. Okay, in general quantum field theory, relativistic quantum field theory. But in the conformal field theory, the stress tensor, in addition being symmetric and conserved, is also traceless. Okay, classically. But with quantum corrections, the trace of the stress tensor can develop anomaly, okay? Such as which takes the following form in 2 dimension and in 4 dimension. This R and the E4 and W squared are curvature invariants in the corresponding dimensions. And the anomaly is captured by the coefficient C2D in 2 dimensions and A and C in 4 dimensions, and their generalization to higher dimensions. These conformal anomalies, as the name suggests, are anomalies for conformal symmetry, but equivalently, they can also be detected by a Weil transformation of the partition function when coupled to a non-trivial background metric as follows. Okay, these conformal anomalies are very universal and important quantities in the CFT because they count degrees freedom in the CFT. Okay, so if you so it takes intuitive values for boson and fermions and also for interacting systems. And they also determine universal parts of, say, Casimir energy of the system, the vacuum energy of the quantum system, and also entanglement entropy. And they also encode various pieces of the stress tensor correlation functions, 2-point, 3-point, and so on. And for example, the 2-point function of the stress tensor in general dimensions is completely fixed by the C-type conformal anomaly. And because they enter into these correlation functions, the lower point correlation functions, they're also very important inputs for running the bootstrap program, which allows one to solve the higher point, more complicated correlation functions. Another very important feature of these conformal anomalies is that they fit into this nice landscape picture. Okay, the conformal A anomaly, which is a conformal A anomaly, which correspond to the confusingly correspond to the C anomaly in 2 dimensions, is known to decrease monotonically under RG flow. And this gave rise to non-perturbative constraints on RG, and also makes rigorous this landscape picture by essentially identifying the altitude with, or height with the conformal A anomaly. Okay. Now, if we also take into account these defects, we discovered that if we zoom into one of these fixed points, there's a finite structure of the landscape. So at a d-dimensional fixed point, the lower dimensional defects organize into like another landscape of RG trajectories with its own lower dimensional critical fixed points, which are described by conformal defects. Now, so conformal defects are defects that preserve a lower dimensional, preserve the conformal symmetry. Sorry, the breaks part of the bulk conformal symmetry, but preserve some lower dimensional conformal symmetry, SOP, 2, for a p-dimensional conformal defect in a d-dimensional CFT. These defects capture some novel critical phenomena of lower dimension of the CFT in the presence of, say, defects and boundaries. Okay? And similar to the case of CFTs, usual CFTs, they correspond to now universality class of defect RG flows. Okay, and it has, as I mentioned, it has this kind of symmetry despite that, but importantly, it doesn't have a local stress tensor, p-dimensional stress tensor, or p-dimensional currents on its volume, and this is the important difference between a defect and the local CFT. The presence of defect also introduced some new critical exponents and the new OPE data into this extended theory. The bootstrap constraints that is well established in the CFT has a natural extension when you include defects, and these constraints are just starting to be explored in these papers. And these equations, I mean, this problem, solving the bootstrap problem is well formulated, but in practice, it's a very hard problem. Okay? So one way to proceed is to extract some additional inputs to put into the bootstrap equations and reduce the unknowns. So one of this potential thing that could help are this other important tool that I mentioned to solve for the IR physics, which are these RG invariants coming from Defect anomalies.
Can I ask you on a previous slide? Those statements must be true for some particular problems. I mean, I can certainly imagine a CFT with a defect on which the low energy field theory is also a CFT and has local T mu nu, wouldn't you?
Yes. So I'm saying generically. So of course you can stack your defect with some local degrees freedom, and those local degrees freedom we have a stress tensor by themselves. Yes. I'm saying that generically, you wouldn't have, even if you have this residual symmetry, there's no local Noether current on this defect world volume.
Well, I don't know what generic means. Actually, I'd say the other way around. You know, generically, defects violate certain symmetries of the bulk theory.
Yes.
And because of precisely of those violations, there are Nambu-Goldstone bosons on those defects. Again,
so that's a very, very important distinction I want to make. So there's no Nambu-Goldstone boson associated with defect. What you have in mind are this, for example, domain walls of finite tension. So in those cases, you have this Nambu-Goldstone boson, which are dynamical. Yes. But here, the defect, you can think of it as domain walls of infinite tension. So there's no Nambu-Goldstone bosons in this case.
Okay, so then your statement is about defects that explicitly violate certain bulk symmetry.
That's right. That's right.
Explicit violation. Okay, so that's right. Well, that's what I'm saying. Some specific context it should be true, but
so that's my definition of defects. So defects always explicitly break the translation symmetry. I should have been clear. Yes.
Well, you started about with some physical systems which don't necessarily do that. I mean, right? So
the example that I mentioned all do this. So, for example, the Kondo effect explicitly breaks the translation symmetry because it's an immobile defect. Also, the heavy quark in quark-gluon plasma also explicitly does this.
Well, the D-branes don't do that, actually.
Sorry?
But the D-branes don't do that.
No, yes, precisely. So I made the statement that precisely what I meant by that statement is that they correspond to a boundary on the world sheet. So it's true that D-branes are dynamical, they have finite tension. So I should not think about D-branes as defect in space-time quantum gravity. But from the worldsheet perspective, these are defects in the sense of their Carty boundary states for the worldsheet CFT. So that's a very, very good point. Does it make it less confusing?
Well, I don't think it was confusing for me. I'm just asking what was the scope of the statements that you are making. And the D-branes are, one way I can look at them, are solitons of the supergravity. So yes. They're not breaking explicitly anything. they are breaking spontaneously, and that's why we can count the number of degrees of freedom on them, and so on and so forth.
Very good. Yes, yes, yes. I completely agree. I completely agree. So when I say D-brane correspond to defect, I meant from the worldsheet perspective. They do not correspond to defect from the target space perspective. From the worldsheet perturbative string theory perspective, D-branes correspond to boundary states for the worldsheet string theory.
Yeah, of course. And then there are precisely the places where you do have, well, generically, I would say, the local T mu nu on those.
No, T mu nu, in that case, it's even trivial. It's just 0 because it's 1 + 1 dimensional. I'm talking about the worldsheet perspective. I think we're mixing up target space with worldsheet.
I'm talking about the word volume of a D-brane. If I take a 3-brane, on it, there is n equals supersymmetric.
Yeah, but it's not talking about that, right? I mean, it's just saying take a 2-dimensional.
Yeah, right.
Yes,
and put a boundary and put a boundary condition.
Yes, right.
Yes.
Yeah, I think what that even means that you don't consider the low energy effective theory for type 2A or type 2B, or consider some space-time supersymmetry or D-branes. You just stake yourself on the worldsheet, the perturbative superstring theory on a 2-dimensional worldsheet CFT. Then the D-branes will be, and his definition will be, like, strictly speaking, a defect, but not something like that, if I understand right.
So it's an Ishibashi state. Is it like an Ishibashi state?
It is an Ishibashi state, yes.
But then that's not a full spectrum of the theory we're talking about.
No, I'm not talking about, yeah, I'm talking about the worldsheet string theory, yes. Perturbative worldsheet string theory. D-branes are non-perturbative objects for a reason. I completely agree with you from the target space quantum gravity perspective. D-branes are dynamical, they're not defects. Whether quantum gravity has defects, such as boundaries, is another question. So for example, in the M theory, the Harari-Witten domain wall, sorry, the Harari-Witten boundary could be a defect. Yeah. Yeah, thanks for, yeah, I should have been clearer on this point for the D-brane. I understand it's right. The way I said it, it could be confusing. Shall I continue?
Yeah. Yes, please.
Thank you. Right, so I was just getting to the point of the other important physical quantity that we can extract to infer non-perturbative physics at the IR in the IR regime. These are the so-called Topf anomalies. Okay, so just to give you well, probably everyone knows what Topf anomaly. Well, so just to remind you what Topf anomaly is. So the simplest case is to consider this kind of triangle diagram with some external currents. I emphasize these are global symmetry currents, which are not gauged. And if there's non-trivial contribution to this diagram, it translates to a divergence, non-vanishing divergence for the current when you couple this current to some non-dynamical background gauge field A with field strength F. Okay, so it takes the following form. And equivalently, if you compute the variation of the partition function in the presence of this gauge field under background gauge transformation, it also shows up as the gauge variation of the log of the partition function. Okay. I want to emphasize these Topf anomalies are different from the familiar gauge anomalies or APJ anomalies in high energy context, in that it's not a thickness of the theory because the symmetry is not gauged, but rather it encodes fine structures of the symmetry. Equivalently speaking, the Topf anomalies are obstructions to gauging. So once you gauge them, it becomes the same thickness as the gauge anomalies. And these obstructions encodes subtle information about the current algebra itself.
Yeah, I understand the terminology you are using, but I objected to the previous speaker, and I should mention it here too. This is the Bell-Jakiva anomaly period. This is a triangle that people calculate in 1969, and it was also for external current. It was for a pion decay. It has nothing to do with the thickness of the theory. That they were calculating the pion decay into 2 gamma. No, no anomalous behavior of theory, no unitarity violation, nothing like that. And that's what it is. So whether it's an external field, it doesn't matter what you attach to the triangle in those 2 points, because what you attach doesn't participate in calculation of the triangle. Only the vertices do. So I'm sorry.
No, I agree. Yeah, I agree. The computation-wise, yeah. So I apologize. This terminology. yeah, this terminology is, I probably just borrowed the terminology that in the recent literature, and this has been what people is using, is probably not quite fair. But yes, it's the computation-wise is very much like the ABJ old story. Yes, I agree. But I think the reason that people call it Toft anomaly is to try to distinguish from the ABJ anomaly, which is often associated with explicit symmetry breaking of this currents because of the
massless quarks, the pion decay to 2 gamma. That's what they calculated.
Right, but the way we learned in like quantum field theory textbooks, oftentimes ABJ anomalies is discussed when we talk about how the, for example, axial symmetry is explicitly broken in QCD, right? When you couple to SU2, when you couple to SU3 gauge fields.
But when you say explicit would be broken if the quarks are massive, right? So anomalous breaking is what you have here on this slide.
Yes, yes.
I mean, again, speaking of terminology. So
I mean, it's an old story, okay, but I mean, it's a bad name. It should be Toft anomaly matching. And
yes,
right. Yeah, I'll talk about yeah. I think it's probably coming from Toft anomaly matching. Yeah,
that's exactly right. Actually, Toft anomaly matching. The anomaly was discovered, before Toft.
Yeah.
Yeah, I think the Greg means
probably,
here, if you want to say explicit breaking, Greg wants you to say the meaning is that you have an explicit extra term which break the global symmetry, right? I think that's what Greg means by the explicit.
Yang is right on the point. So explicit breaking means if quarks are massive in the Lagrangian, that's explicit breaking of your chiral symmetry.
I think Yifan means explicit breaking here, it means that it's not spontaneously breaking by some vacuum configuration.
No, yeah, what I mean by breaking, it's just when you have the triangle diagram, even when the quarks are massless, but when you have a triangle diagram for the one direction being the axial and the other being the SU3 current, which is gauged, even when the quark is massless, when you gauge the SU3, explicitly break the axial symmetry.
Yeah, of course, but that's anomalous breaking.
Yeah. That's what I meant.
Of course, yeah.
So just to distinguish from that case, I think people use this somewhat unfortunate terminology.
I apologize for this, terminology things, but sometimes they are important. So I didn't mean to interrupt too much.
Yeah. All right. No problem. Okay. So sorry, I'll keep using this terminology, but so there are several nice properties of this Toft anomalies, which is what makes it particularly useful. Is that it's constant under RG. Okay. So under RG flow, the Toft anomaly doesn't change. And this is because the Toft anomalies are typically, they're quantized and discrete, so they do not change under continuous deformations. And for a similar reason, they're robust. Okay? And because they do not change RG, one can use the anomaly matching, which specifies that the UV and IR anomaly agree for RG flow that preserve the relevant symmetry. Now, anomaly matching allows us to put non-perturbative constraint on IR physics, given the UV description. So there are many examples where this is very powerful. So one particular example is the antiferromatic SU2 spin 1/2 Heisenberg chain. So in that case, there's a charge conjugation symmetry that's coming from some Z2 translation on the lattice, the one-dimensional lattice. And anomaly of that charge conjugation symmetry implies the IR phase of this spin chain has to be gapless. So it really depends on the fact that this is spin 1/2 chain versus a spin integer spin chain. And with some more work, you can actually prove that the IR phase has to be described by some SU2 level 1 WZW model. Okay. And another example, for example, in QCD is that you have for SU3 QCD with say NF quarks, the chiral SU-NF symmetry have a chiral anomaly. And using this non-trivial anomaly, you can show that confinement in the QCD will necessarily imply chiral symmetry breaking. Okay, so some simple exercise you can work out. Okay, so what are the kind of, well, given this success of anomalies in constraining RG flows and helping to solve IR physics of ordinary QFTs, we certainly want to extend this to the context of defects. Okay? So what are the kind of main questions I want to ask and address here? So one question is to explore, like what is the general structures of anomalies in the presence of defects? And another thing I want to express is how to determine universal quantities of defects, such as the defect new anomalies, like defect conformal anomalies, and understand the kind of RG constraints that they will give rise to. And furthermore, we want to understand how does the old anomalies, 12-R APJ anomalies, constrain the spectrum allowed defects. So I mentioned that there are distinct classes of consistent defect spectrum associated with a given local operator spectrum. So this question kind of touched upon on that point. So whether old anomalies in the bulk constrain what kind of defects you can have. So as we'll see, there will be non-trivial constraints. So let's move on to the first point, which is about new kinds of anomalies that arise from defects. So, just to remind you again, so defects generally in a d-dimensional quantum field theory is some extended operator defined on the p-dimensional submanifold sigma, and this defect is defined by this curly D. And defect anomalies correspond to, so just as anomalies correspond to modification, quantum modification of the conservation laws of Noether currents, defect anomalies correspond to modification of this conservation laws of Noether currents localized on the defects. This is what this delta functions mean. So these defect anomalies are localized on the defect. Okay, they're zero everywhere else, but they localize on the defect. So here, this F are the field strength for the external gauge field that coupled to this conserved current in the bulk, and this R are curvature of the metric that coupled to the stress tensor. Okay, then K is the traceless part of this of the extrinsic curvature associated with this defect submanifold relative to the bulk. The form of this right-hand side can be fixed by exploring some algebraic constraints on anomalies, known as the West-Zumino consistency conditions. And I want to emphasize this kind of defect anomalies can be present even if the bulk currents and stress tensor has no anomaly. So for example, you have an odd-dimensional quantum field theory, odd-dimensional conformal field theory, there's no conformal anomaly, and there's also no perturbative anomaly associated with some conserved current. But on the defect, inside this odd-dimensional quantum field theory, there could be non-trivial defect anomalies. Okay? And this defect anomaly coefficients, just like what happened in the bulk, and they encode non-trivial information about the correlation function of bulk operators in the presence of this defect. Okay, so the defect, as I mentioned, is part of the extended operator algebra. So this anomaly coefficient encodes correlation function that involve this extended defect operator, as well as other local operators, in this case, correspond to the current and stress tensor. So just to look at the surface, so I should say that for a concreteness of discussion, I'll focus on the case here, p equal to 2. So this describes surface defects. Okay, so just to be a little more concrete. So consider the surface defect, say in a d-dimensional conformal field theory. The anomaly takes the following form, as I mentioned. So I just want to emphasize again that this differs from the usual 12th anomaly in the sense that the anomaly is two-dimensional for a surface defect. It's localized on the surface where the defect lives, but it's an anomaly associated with a current that's of d dimension. So the current propagates in the bulk. Okay, but still it shares many features of anomaly for like usual d-dimensional quantum field theory. In particular, the anomaly is an obstruction to gauging in the presence of a defect. And the anomaly coefficients are also robust against deformation on a defect. And they gave rise to RG invariance under defect RG flows. And in some cases, this defect of anomaly can be computed by bulk inflow and potentially from defect degrees freedom that localize on a defect. So this is just to show you some examples which you can, for the free fields where the defect anomaly can be computed easily, and I've tabulated here. So there's a similar story for the conformal anomalies of defects. In this case, the Noether current, the relevant Noether current is stress tensor, and the defect anomaly correspond to a localized modification of the tracelessness of the stress tensor, localized on the defect over volume. So here we'll be interested in this particular anomaly coefficient known as the B coefficient, which is analogous to the C conformal anomaly for 2D CFT. This coefficient, similar to what the C anomaly measures in 2 dimensions, it measures the degrees freedom on the defect, but in the relative sense. For free fields with Lagrangian boundary conditions, like a free scalar field with Dirichlet boundary condition, with Norman boundary condition, or fermions with the standard boundary condition that involve these chiral projectors. the values of this the value of these anomalies, this defect conformal anomalies, can be extracted from the hit kernel methods. But one would like to understand what happened to the interacting cases. Can we also determine the conformal anomalies in some other cases, in the interacting cases? And more generally, one would wonder whether there's a monotonicity theorem associated with defect RG flows where this anomaly coefficient decreases monotonically under the as you tune the RG scale.
Is R lower defect dimensional or bulk dimensional?
So this R is the Ricci curvature scalar on the defect.
So it's lower dimensional. Okay.
Yes, it's two-dimensional. Yes.
And
so, very good question. So as you see, the two terms has very distinct qualitative features. This first term is intrinsic in the sense that this R just depends on the two-dimensional metric intrinsically, but this D term depends on the extrinsic curvature. So it depends on how the surface is embedded into the ambient spacetime. Right. Very good question. And this is also why this B is more relevant for counting integration freedom on the defect, while D encodes some other information. And this is also kind of intuitive why B would play the role of this height function for defect RG flows rather than D. So this is so regarding the RG monotonicity, the kind of problem want to consider is to start from some UV conformal defect. Okay, sorry. And you turn on some relevant information by some defect operators that lives on the defect, this OUV, okay? And you consider this RG flow, which is described some defect field theory, that flows to some IR conformal defect. And the question is whether certain defect anomaly A, or sorry, it should be correspond to B here for the surface defect, decrease monotonically under this RG. And I'll spare you the proof, but the answer is yes. In 2 dimensions, it was proven by this gentleman in 2015. And it was proven in 4 dimensions by my work that appeared last night by extending the previous work from, it's an easy extension of the previous work from Komogazki and Schwimmer in 2011 that applies to 4D QFTs. Okay. But the consequences is interesting. Apart from showing that defect RG flows are monotonic, it also gives a nonperturbative diagnostic on possible IR phases of RG flow, defect RG flow. So it tells you that among the possible candidate IR defect, the IR conformal defects you can come up with, they must satisfy the relation that their conformal defect conformal anomaly is smaller than that of the UV conformal defect. So, but to kind of make use this kind of a non-perturbative tool in practice, we need some way to estimate the conformal anomaly of this candidate IR conformal defects that are not described by some free theory with like dirichlet or Neumann boundary conditions. So this requires, so this leads to this question, which is to kind of how do we determine conformal anomalies for some strongly interacting defects? Okay. This is where the supersymmetry becomes useful. So conformal defect with supersymmetry has an even larger symmetry known as the superconformal symmetry, just by how the algebra close among themselves. And for surface defect, this superconformal symmetry includes in particular U1R symmetry. And this U1R symmetry current, which is the current lives in D dimension, emphasize again, is related by the preserved supercharge to the D-dimensional stress tensor. So correspondingly, the defect conformal anomalies associated with the stress tensor, the trace, is related by supersymmetry to the Toft anomalies. Okay. And this kind of non-perturbative, this supersymmetry relation gave a non-perturbative relation between the easy to compute RG invariant quantity, the Toft anomalies, to the difficult to compute RG variant quantity, the conformal anomaly, okay, at the fixed point, through what's known as some anomaly multiply relation, which I derived. Okay, so this provides kind of a very efficient way to extract the conformal anomalies of superconformal defects using the Toft anomalies. So let's just put this machinery into a simple example. Let's consider one of the simplest superconformal field theory in 3 dimensions, non-trivial superconformal field theory in 3 dimensions, the super Ising CFT. This CFT has a UV description, which is very simple. it's described in terms of one chiral multiplet. The chiral multiplet means a complex scalar plus a Dirac fermion in 3 dimensions, and described by superpotential, cubic superpotential. And what this means is that you have the simple Lagrangian, which includes some 5⁴ potential, some fermion terms, and some Yukawa couplings between the fermions and the boson. This theory flows to injecting 3-dimensional CFT in the infrared. And this theory also appears, surprisingly or not surprisingly, in various condensed matter setups. For example, it can be engineered in a certain optical lattice of cold atoms. It also appears at the boundary of certain topological superconductors. Okay? So the question we want to address here is, what can we say about its boundary universality classes, in particular the defect conformal anomalies? Well, it's easy to use our method. So here, to illustrate, I consider the simplest boundary condition, which is interacting, emphasized, even though it looks like it's not so. It's because the bulk coupling is, there's a non-trivial bulk interaction. Okay? So consider the simplest boundary condition that's described in UV by this supersymmetric version of the Dirichlet boundary condition that you impose on the scalar and on the fermion. As I mentioned, for this case, the conformal anomalies will be determined by the 't Hooft anomalies, using the SUSY anomaly multiplet relation. The 't Hooft anomaly, because it's robust under deformations, can be obtained by turning on, say, a mass deformation in the bulk, such that the theory becomes free. And in the free phase, we can certainly compute the 't Hooft anomaly coming from the fermion, and it gives this simple answer. And because the 't Hooft anomaly are invariant on this mass deformation, we can go back to the fixed point and use the anomaly multiplet relation. And this will give a prediction for the defect conformal anomalies associated with the superconformal defect that's coming from this UV description. Okay, and corresponding, as I already mentioned, this will determine the boundary Casimir energy associated with the corresponding defect, as well as boundary entanglement entropy, as illustrated in this diagram. What about some general constraints? So I've told you about how these various new anomalies are brought in life by the presence of defects, and how to determine some of these anomalies using tools, analytic tools like supersymmetry. Let us now switch gears and investigate what kind of constraints the old anomalies, 't Hooft ABJ type anomalies, have. What kind of defects are admissible in the QFT defined by a given local operator algebra. Okay. So just to remind you again, sorry for the naming, that if it's imagine you have a theory with a symmetry G, okay? The presence of usual 't Hooft anomalies, say in the absence of boundary, corresponding to this triangle diagram, implies that there's an obstruction to gauging the symmetry G. So it turns out that, as proved in general cases in this paper, in our paper that appeared last year, and in 2 dimensions for continuous symmetry in these papers, that 't Hooft anomalies associated with this triangle diagram of this type and generalizations in the presence of boundary, okay, would imply that there's an obstruction for a G-symmetric boundary condition. To set it differently, if you have a theory with symmetry G and there's a non-trivial anomaly for the symmetry, there do not exist boundary conditions that preserve the symmetry. Okay. In other words, the symmetry must be broken. The anomalous symmetry must be broken at the boundary to a smaller subgroup such that the anomaly is trivialized. Okay. This also applies to G. This applies to G being Lorentz symmetry in addition to global symmetries. This explains why it's very difficult to realize, in experimental setup system with gravitational anomalies, because in experimental setups you want to have boundaries, but as I explained to you, system with gravitational anomalies cannot have relativistic boundary conditions. Okay, so let me skip the derivations view of time. Just mention that this kind of obstruction does not just apply to the ABJ type anomalies, which are defined for conserved currents. They can be extended also to discrete symmetries and its corresponding anomalies. And these anomalies are captured by some group cohomology, and their further generalization. The technicality is not important, but they just want to say that the kind of method that we use to prove these things can be extended to these discrete symmetries, and the same result carries over. So for this talk, I think we just need to remember that the slogan that anomalous symmetries in the quantum field theory must be broken at the boundary. Okay. So perhaps it's more interesting to look at some specific applications of this of our general result. So one particular example is the boundary conditions of is sometimes known as the harmonic oscillator of 21st century, the interval superamials. Is a somewhat close cousin of the four-dimensional QCD, but with encoded for supersymmetry and adjoint matter. So this theory famously has a global symmetry, also known as R symmetry, SO6 R symmetry. And there's anomalies associated with symmetry because the theory has a Lagrangian. You can compute these anomalies by hand, and you see that there's a ABJ type 12th anomaly for this symmetry, which is computed by this triangle diagram. Okay, is associated with the the anomaly arises because this is non-trivial cubic Casimir for this SO6 R symmetry. And in addition, if you look at this maximal subgroup of SO6 R symmetry, include this SU2F vector. This SU2F vector is known as the flavor symmetry of the interval superamials, thought of as the include 2 superconformal field theory. This SU2 flavor symmetry in that description has a Witten anomaly, which is coming from the large gauge transformations associated with SU2 on S4. Sorry. Okay. And from our general results, which says anomalous symmetry must end on the boundary, must be broken on the boundary, it means that either SO6R preserving boundary condition or SU2F preserving boundary condition do not exist. Okay, and indeed, if you look at known examples of maximally symmetric boundary conditions, for example, the one studied by Galto and Witten, they only preserve this other maximal subgroup SO6, other maximal subgroup SO3 times SO3. And this has for example, this has only a abelian intersection with this SU2F. So the Witten anomaly trivializes. And you can also compute that this perturbative cubic anomaly trivializes for the subgroup as well. Okay. A slightly non-trivial case comes in when you study the boundary conditions of two-dimensional fermions with chiral symmetry. So the symmetry relevant symmetry here is the chiral parity symmetries, the left and right fermion number symmetries, Z2L and Z2R. This has a subtle anomaly, the ZA class, that's studied by Fedovsky and Kitaev in 2010. This anomaly is beyond this group cohomology type that I mentioned. The detail is not important. What you just need to be, what's important here is just that if you have NF number of Mariana fermions in 2 dimensions, left and right, this anomaly is only trivialized if NF is a multiple of 8. Okay, and then from our general theorem, it implies that a symmetric boundary condition of symmetry under this chiral fermion number symmetries is only possible if the number of flavors is a multiple of 8. And indeed, very recently, in 2010, explicit constructions of symmetric boundary states for 2D fermions, which is a simple exercise you can do, but you have to do it thoroughly, shows that such boundary conditions preserving the symmetry is only possible if NF is a multiple of 8. Okay, but it's a systematic analysis you have to go through, but we have a very general statement here. A more non-trivial case is coming from SU2 adjoint QCD in 4 dimensions. So in this case, the relevant symmetries are the one-form symmetry because you have adjoint matter. There's a non-trivial one-form symmetry coming from the center of SU2. There's also a time reversal symmetry. The time reversal symmetry is preserved. So this theory has a theta angle, as you know, and the time reversal symmetry is preserved as 2 distinguished values of theta angle equal to pi and theta angle equal to 0. But the realization of these symmetries at different theta angles differ by the value of the mixed anomalies. Okay, so these 2 symmetries may have a mixed anomaly. This anomaly is non-trivial, Z2 value mixed anomaly. This anomaly is non-trivial for theta angle equal to pi and trivial for theta angle equal to 0. Now, this domain wall, upon folding, can be mapped to boundary conditions for the double theory. Okay, and this anomaly added up if you focus on the diagonal Z2 times time reversal symmetry. And then our general theorem predicts that if time reversal symmetry is preserved, because of the presence of this mixed anomaly, the one-form symmetry must be broken on this boundary, and correspondingly must be broken on the domain wall. This implies there must be deconfinement on this time reversal symmetry preserving domain wall. Okay, Let me conclude. Let me conclude. So I hope I have present you enough evidence that shows that defects and anomalies are important features of quantum field theories. In particular, defects appear in a wide range of quantum systems. They appear as boundaries and impurities. And I've also argued that anomalies are very robust variables, observables of strongly coupled systems. And both are essential for the modern understanding of QFTs. And in particular, if you explore interplay between anomalies and defects, it gives rise to various non-perturbative constraints on the extended operator algebra. They involve defect operators as well as local operators. In particular, the defect conformal anomalies obey the so-called A theorem, a defect version of the A theorem, which proves that the RG flows localize on RG flows on the defect coming from defect perturbations is monotonic. And also, I've introduced you some non-perturbative tools to extract defect conformal anomalies, this important physical observable for this defect conformal field theories in the presence of supersymmetry. And also, I've discussed how bulk Toft anomalies will constrain or obstruct symmetric boundary conditions. There are many future directions. Okay, one future direction is that it's about this generalized symmetry. So the notion of symmetries and its anomalies have been constantly evolving. So recently, there's this further generalization of symmetries by topological defects. So topological defects are, in the ordinary case, topological defects correspond to integral of the Hodge-2 of the Noether current on some codimension 1 manifold. And this Noether charge can be generalized because the topologicalness of this Noether charge coming from the conservation law of the current. And this can be generalized to general topological defects. And a quite big jump, logic jump, is to consider topological defects that are no longer invertible, that no longer obey group law under fusion. And these are this non-perturbative defect that's explored in a serious paper, including myself and my collaborators. This gave rise to the so-called categorical symmetries, which also have some applications to two-dimensional 1+1 dimension QCD in these very nice recent papers. Okay. And some other thing that I've been exploring recently is the classification of defects based on general principles. So once again, this is regarding this point that I mentioned, that given a consistent set of local operators, there may be constraints on the defects you can add. So there may be distinctive classes you can add. And here in this with my collaborator Nathan, we have explored this in the context when the defect preserves supersymmetry, various amounts of supersymmetry. Okay, from general principle like unitarity, locality of the defect bulk couplings, and the symmetries. And also in cases with enough supersymmetry, one can determine quite a bit of the extended defect local operator algebra exactly using the localization method. And this have been explored for superamials in the number of papers from myself and from collaborator Shota Komatsu, and recently have been explored in 6 dimensions. That's 2 here. So let me just mention another potential interesting future direction that I recently found interesting is the context of, it's one of the most well-studied boundary critical phenomena in the old days, namely the boundary universality class, the ON symmetric boundary universality class of 3-dimensional ON models. Okay, so this have various experimental implications because the ON models are relevant for describing the universality class associated with liquid magnets and so on. Okay, and this model is known to exhibit very rich boundary critical phenomena. So at temperature Tc, the bulk ON model becomes critical, and this line describes various boundary phase transitions. Okay, so the H corresponds to some boundary coupling you can tune, or boundary mass essentially. Okay, so this very simple model has a very rich boundary phase transition structure. So in this, so here, what I want to suggest, and what I want to explore is the similar boundary universality class and the phase transitions for the super Ising CFT. So in that case, we have more tool, using the non-perturbative relation that I derived from supersymmetry. In those cases, we can try to classify the superconformal boundaries that correspond to this universality classes, and we can extract the boundary conformal anomalies exactly using these anomaly multiply relations. And with those in hand, we can try to understand the boundary phase transitions. And finally, it will be very interesting to kind of extract lessons for the non-supersymmetric case corresponding to these OM models. I think I'm over time. So let me just end here by listing another number of other interesting future direction, a number of other future directions I find interesting, and invite questions. Thank you for your attention.
Thank you very much for the nice talk. And I mean, of course, you can take time. So one thing that maybe I wanted to ask, and then I'll leave it to others, is when you talk about discrete symmetries and the symmetries that were not associated to homology, what do you mean by that?
Oh, right. So the let me go back to last
anomalies slide. In that case.
Right. So the symmetries. So the symmetries I talk about here is always associated with some Noether charge. So it could be discrete. On this slide, it could be discrete. It could be continuous. But the anomalies may not be always associated with cohomology. This is what I meant. So the usual case when the so for global symmetries, if the symmetry is discrete, the anomalies is classified by this cohomology. But if you consider kind of mixed global symmetry gravitational anomaly, those are generally captured by certain generalized cohomology theory, sometimes known as the Bordism theory. So this is what I mean. Yes.
How do you compute those anomalies? I mean, how do you find that they are not vanishing?
Right. So the anomaly that so usually for continuous symmetry, one way to see the anomaly is to compute the variation of the Penning function under some background gauge transformation. Right. For this group cohomology anomaly, you can do something similar. So you just couple to some discrete background gauge field, and you look for variation of the Penning function under this discrete gauge transformation. But for this case, what you need to look for is some kind of manifolds. So you want to suppose you start with a manifold. You want to look for you want to compute this Penning function on the given manifold, and you want to compute the same Penning function on a different manifold with a different structure, and you want to compute the two, compare the two. So, for example, if two manifolds are related by some large diffeomorphism, okay. And if the Penning function differ, that means that there's a gravitational anomaly. And if you decorate this Penning function on top of this non-trivial geometry, decorate this Penning function also with gauge fields, background gauge fields for discrete symmetries, and the difference between this Penning function will tell you about mixed gravitational and global symmetry anomalies.
Thank you.
Yeah.
Other questions?
Yeah, can we go back to that interesting example you had, SU2 with adjoint?
Of course, yes.
Yeah, so it went a little fast, so I wanted to grasp this.
Yes, yes.
So on the domain wall, you get a deconfined phase. Is that what you get?
Yeah, so I'm saying that if the domain wall preserves time reversal symmetry, it has to be deconfined, yes.
Time reversal along the okay, time reversal, okay, good. And yes. Deconfine, and what's the theory? I mean, what's the symmetries?
I don't know. This is just the general prediction. Yeah.
Okay, but
we haven't investigated what the candidate theory is. Yes,
right.
That's a very good question. But...
Okay, good. So this is 4-dimensional. To starting point is 4-dimensional.
That's right.
Okay,
that's right.
But that must be very close to n=1 super Yang-Mills.
Yes.
But probably something detuned.
That's right. That's right. Yes.
But in that case, you can find a solution for the domain walls and probably address.
That's right. Yeah, I'm sure. I only know. I mean, Vafa, Acharya, they studied the domain walls, but not for this Janus type where the theta angle jumps. In that case, it describes some transformance theory on the wall. So here, yeah, it will be very interesting to actually study what the domain wall theory is. Yes. Yeah. That's a very good suggestion. I agree. Yeah. Thank you.
Other questions?
So I'm asking, it's I think closely related to what Greg was asking before, because there are kind of two notions of defects I'm talking about. One is the defect operators you're talking about here, and another is kind of topological, dynamical topological defects like domain walls, like vertex strings and stuff like that. So basically, what is the relation between the two? Like for instance, for local operators, we know that you can also talk just about local operators, but then you look at correlators and look at LSD poles, and those LSD poles tell us the presence of particles, dynamical particles.
Yes.
So is there an analog of this in this story?
So I guess one thing I can say is just there's no Goldstone boson associated with this defect. That's the main difference. So the symmetry is really explicitly broken.
Right, but sometimes these defects, like they do create real dynamical objects in the theory, like for instance.
They do, yes,
like,
that's right.
So how to like for instance, Wilson loop in confining in theory creates confining string.
That's
so
right.
So how to distinguish these two situations when defect operator just doesn't create anything, and from situation when it does create actual dynamical?
It always create things, right? I mean, it always give you a state. I mean, you
right.
can always, right? You can always imagine like a sphere that includes your defect, and you quantize your theory on this. I mean, in the conformal case, you can quantize theory on the sphere, and that correspond to some state in your Hilbert space. So it always creates something. I guess the question is whether the something has some interpretation as extending objects. Is that
right? Exactly. So in one case, there is really lower dimensional object than which exists in the theory and which is created by
that's
this.
Right. That's a very good question. So yeah, that's a very good question. Right. Yeah, I think there are cases where the presence of this was, for example, line operator does not indicate they're actually strings in the spectrum.
Right.
Yeah. So that should be some extra criterion on the defect.
Mm-hmm.
Right. Interesting. That's an interesting point.
Any other questions on any level for any aspect of this talk? Well, I mean, in your talk, you had, did you, in the examples better that you gave, yes, were you also discussing cases where there is no Lagrangian description, or at the end you always had models with the Lagrangian description and with operators?
Yeah, very good. So, so I wanted to be concrete. So I talked about like examples with some UV Lagrangian descriptions. So I have extra slides. So if you wish, you can study totally non-Lagrangian examples. For one example is the 6-dimensional ICFT, and there are surface defects in this theory, which also do not have Lagrangian descriptions. But their top anomalies can be extracted from anomaly inflow, okay, in M theory by considering, because surface operators are coming from M2 brane intersecting with M5s in this picture. And their anomalies can be determined by anomaly inflow with anomaly polynomial of this form. And then using this general anomaly multiplicity relation, we can determine these conformal anomalies. So they're completely bypass Lagrangian. And then this answers in a large N limit. And for the SUN type 2,0 theory have been reproduced. Well, it was previously computed using, it was some lengthy analysis in ADS-CFT from these authors. The whole paper is about computing this thing in the large N limit for SUN theory, but it's just like a couple line analysis from this general relation. But I thought this will be 2,0 would be too technical for general talk. So yeah.
Thank you. And actually, yeah, what do you mean by holographic duals of the defect?
Yeah, so here the last slide, many of the future directions, I think I have to thank you guys. I came up with these things while preparing for this talk. For example, here is that if you consider a CFT with this defect in the holographic context, when the theory has a holographic dual, then this defect also has a holographic dual, right? So suppose you have some boundary. This will correspond to a boundary that would extend into the ADS bulk, and potentially have dynamical gravity on this, this boundary in ADS. Okay? And it'll be interesting to identify what kind of gravity that lives there. It could be of the Randall syndrome type, or it could be of this DGP type with some dynamical Ricci scalar term. And another interesting question that I came up, I guess, last night was that there are potentially interesting constraints. It's related to what Greg asked, to actual defects in quantum gravity. So imagine you have you have 10-dimensional type 2B string theory, the complete theory. We don't know if this quantum gravity has boundary, right? But if it were to have a boundary, say, which is 9 dimensions, which preserve the 9-dimensional, Poincare symmetry, in the ADS safety correspondence between type 2B on ADS 5 times S5 and inverse Biamils, this putative boundary wrapping the S5 should correspond to a boundary of the inverse Biamils. And because this boundary in 10 dimensions preserve the the 9-dimensional Poincare symmetry, naively and it wraps the entire S5. So I would expect this boundary, when you look at it from the 4-dimensional inverse Biamils perspective, should preserve the entire SO6 symmetry. But I told you that the SO6 symmetry has an anomaly. Okay, so the general obstruction tells you that inverse Biamils cannot have SO6 preserving boundary condition. So this argument rules out non-perturbatively such a boundary for the type 2B string theory, assuming ADS CFT, of course.
Again, please ask.
And also, I find this last point interesting, which I learned also recently. I didn't know, I think it's probably my ignorance, that the quark-gluon plasma, the critical point of the quark-gluon plasma, is also described by the Ising universality class. It's probably known to many of you. And then there's this interesting study, bootstrap study of Ising CFT. So we know a lot about the Ising CFT, the critical exponents, the low-lying critical exponents, as well as non-trivial line defects in the Ising CFT. So it'll be interesting to see what these line defects in Ising CFT correspond to in this quark-gluon plasma, and see how it's related to some UV description in the QCD. I mean, there are many interesting line operators in the QCD, but it'll be interesting to see where, how do you kind of translate the signature of this, physics of this IR line defect in the Ising to some kind of UV description. This may have some experimental consequence, I don't know.
Can I just ask a question about maybe the last point? It's also related to what Sergey and Greg asked. So by line defect in Ising CFT, do you mean, so it's let's say like a line of spins where on a certain fixed line, all the spins are up, for example?
So it has to be some kind of immobile spin.
Yeah. So the line doesn't move, right?
That's right. Yes.
Okay.
So the particular Ising defect Ising defect I have in mind, I have been studied by bootstrap literature, is so the Ising CFT has a Z2 global symmetry, right? So you can imagine a Z2 twist line. So which means that if you go around this defect and if you're charged under Z2 symmetry, you pick up a minus sign. So this kind of a Z2 twist defect have been bootstrapped to great precision in bootstrap literature. I don't know what they will correspond to from the quark-gluon plasma perspective. But
so yeah,
since it's the class, it must mean something.
So yeah, in that context, one might, if one thinks about Ising model as like IR fixed point of phi to the 4th theory, then there one kind of, if one perturbs it, then it becomes exactly like double well potential.
Yes.
And then one has dynamical defect, which is domain wall, which interpolates between like two vacuum. So yes. Is it possible to extract information like from this bootstrap CFT bootstrap of Ising defect? Is it possible to extract any information about dynamics of this domain wall, which is actual dynamical object, which is present in the perturbed Ising?
Interesting. So you want to say that this line defect in this symmetry breaking phase actually generates domain walls?
Yeah, one would think, that at least in the UV, that they should correspond one to another, right?
Yeah, right. Yeah, I don't have anything intelligent to say, unfortunately, at this point. But yeah, this is certainly very interesting to think about.
Mm-hmm.
Yeah.
Thank you. Any question? Maybe from students?
Yeah, hi. I was curious, is there a intuitive understanding about like that the obstruction to gauging in the bulk would be accompanied with obstruction to gene invariant boundary conditions, or is that expected somehow? It sounds kind of like the ADS-CFT story, but obviously this is a different context.
Not sure what the relation. One thing I should emphasize is that boundary is different from other defects because it kind of probes more physics in the bulk than other defects. So the argument that we used, for example, that proved the obstruction of symmetric boundaries will not work for higher codimension defects. So I would say vaguely, this obstruction is coming from the fact that all the anomalies in the bulk can be kind of encoded by some data on the boundary. And the fact that the boundary is symmetric will tell you that this anomaly has to be trivialized. Or maybe I can give you a converse statement, which is more intuitive, but does not lead to our result, which is that suppose you have a quantum field theory. We have a system with symmetry G. Suppose the G symmetry has no anomaly, and also suppose that there's a relevant deformation, preserve the symmetry, and flow such that the theory would flow in infrared to a gapped phase, okay, with a single unique vacuum and no interesting physics. And then you can consider a profile for this relevant deformation in the space direction, okay, that goes from plus infinity, from 0 to say plus infinity, and this will give rise to some kind of domain wall between the original theory that you have and this trivial gapped phase, okay? And because the gapped phase is trivial, this is just equivalent to a symmetric boundary. So this is somewhat the converse statement to what we made. That is, if you have a theory with no symmetry G with no anomaly, then you can have a symmetric boundary. I'm not sure if does that help or help with the intuition?
Yeah, I think I'll need to think about it a bit more, but yeah, I think that yeah.
Okay.
Any?
Yes. So about the connection between the supersymmetry and the conformal anomaly.
Yeah. Yes.
In that part. So this kind of can be used as a a rephrase of the A maximization or the C extremization of the 4-dimensional and 2-dimensional SCFT, something
right.
like that.
So actually the 2-dimensional the 2-dimensional C extremization and the 4-dimensional A maximization has natural extensions to this defect anomalies, and this have been proven it's an easy extension of previous results have been proven explicitly in my recent papers.
I see.
So in particular, as you may know, the A maximization gave us stronger results than the traditional A theorem, than the weaker A theorem for supersymmetric artery flows. It constructs explicitly a function and such that the artery flow will correspond to a gradient flow with respect to this A function, the supersymmetric artery flow. So the similar statement would also hold for this defect artery flows preserving this amount of supersymmetry. Yeah, so this I didn't explain. There are various kind of levels of A theorem. There's the weak form of A theorem, which just demands that the central charges between the IR and UV fixed points have this monotonic relation. There's a stronger relation that tells you that there should be a well-defined A function or C function along the entire flow in terms of the local couplings or coupling does not, so the A function should not depend explicitly on the RG scale, but only depend on RG scale through the running couplings. Okay. If such a function exists and match with the conformal anomalies at our UV fixed point, that give rise to the stronger version of A theorem. Now the strongest A theorem would say that actually the flow is a gradient flow with respect to the A function.
I see.
Yeah, this is not proven. This statement is proven in 2 dimensions, essentially by Zamolodchikov. The C function is a gradient. the RG flow in two-dimensional is a gradient flow with respect to the C function as Amalchikov defined along the entire RG flow. But in 4 dimensions, this is only proven for the supersymmetric RG flow, essentially using the A maximization. Extension of A maximization away from the fixed points. This is work from Kutuzov, following the work from Triligator and Wecht.
Any?
Yeah,
question?
may I? Yeah, so so you said that for these defects, so the anomalies are localized on the defects, right?
Right.
I'm kind of worried about here because I mean, if I calculate some path integral or partition function or correlation function
Yes.
in the in the bulk, but I don't, my path integral or I mean the region I do this computation, I don't touch the defect.
If you do the path integral, you cannot.
I mean, no, I'm not pressing. I mean, if I calculate some correlation functions, but I don't touch.
Good. Yes.
But I don't touch the defects. Can I see this anomaly effect in this, these observables or?
Yes. So a very good question. So for this, if I go back to this, anomaly. For example, this anomaly, right? So for example, if this anomaly, this anomaly actually appears in the 2-point function of the conserved current J in the presence of a defect. Now the 2-point function in the absence of a defect, as you know, is completely fixed by the word identity and the conformal symmetry.
Yes.
It's a coefficient. Now, interestingly, in the presence of defect, this is no longer true. There's a conformal invariant ratio now, essentially coming from the distance between the vertical distance between this current and the defect. Now, this conformal cross ratio, if you take it to be such that the operator is far away from the defect, the 2-point function, again, as you correctly said, just given by the 2-point function of 2 currents as if there's no defect. But the dependence on the cross ratio would encode this anomaly. In particular, as you tune the cross ratio such that this bulk operator approach the defect, the effect of this coefficient K will become prominent. So the key is just that the defect correlation functions has a much richer structure than the case without a defect. Of course, it's consistent with the case without defect when you take kinematic limit where the defect is far away.
Okay, I see. Thank you.
No problem.
Yeah, and another question. So here you are considering just, I see in this picture you are seeing that there is one defect object, right? If I consider some I don't know whether this is a crazy configuration, but is there any kind of if I have 2 defects cross each other, is there any ambiguity? I mean, because the maybe the most trivial example I can think of is that zero form symmetry in 2-dimensional CFT, right? Yes. I can have 2 defect lines.
Yes.
I mean, I might be arrange them on a cylinder, one in the time direction, one in the S1 direction, but what kind of, is there any ambiguity or some special treatment you should take here?
Very good. So very good. So in general, when the lines cross, there is ambiguity. Where does the ambiguity come from? It's coming from the fact that you have divergence. So just as you know, when you have local operators that collide, there's divergence, and you have this ambiguity give rise to the contact terms, and it's relevant for the conformal anomalies. If you look at stress tensor colliding, right? Similarly, when this defects collide, there are also ambiguity. So you have to resolve, and when you resolve, there could be different choices you can make, and this encodes this kind of anomalies. The choices that you make, if they cannot be removed by local counter terms, they will give rise to.
Okay. So it's so you're saying that this ambiguity can be, if I imagine it can be encoded in some phase factor in the torus partition function or something like that.
Yes, and
ambiguity
just realized by this fixed factor for symmetries will be some phase factor associated with this 2 different way of fusing this topological defects. This is precisely the picture that's relevant for what you were saying.
Okay.
Yeah.
And the anomaly is encoded in that factor.
That's right. Anomaly is encoded.
Okay.
So,
Okay. I see.
so you can think about this picture as two different ways of resolving the fourfold junction. If you this part and this part. And there's two ways of resolving the fourfold junction into threefold junctions. Can be ambiguous, and this factor would encode the anomaly. Yes.
Thank you. So, do we have other questions? We have been asking a lot of them, so let's thank again our speaker, and thank you, Yifan. And again, if there are no other questions, we'll let you go. Again, it was a pleasure. Thank you for giving this talk.